It's my pleasure to welcome Emily Cunningham for our final seminar of the academic year. Before I talk about Emily, I just want to take the opportunity to thank Jay and Hao for a really wonderful slate of seminar speakers this whole year. And so capping it off with one last excellent speaker. Back to Emily. Emily got her PhD at UC Santa Cruz and then has been in New York City ever since. She came to NYC as a Flatiron Research Fellow at the CCA. She's currently a Hubble Fellow at Columbia University. I just learned that she will be starting a faculty position at BU in the fall of 2025. So we got to make the most while she is here in the relative tri-state area neighborhood. Emily is an expert on our galaxy's backyard, or our stellar halo, in all of its seven-dimensional glory. 7 dimensions are 3 dimensions in position, 3 in velocity, and 1 in chemical abundances. Maybe there are more in chemical abundances. It kind of feels like you're killing the chemists here. She's primarily focused on using the observable tracers of stars to study 2 main things. 1, the dark matter halo of our galaxy, and 2, the dwarf galaxies that came in and deposited those stars in our halo. So with that, I would love to welcome Emily. Please join me and take it away.
Thank you so much for the introduction, Tomer, and thank you all so much for coming today and for having me. It's my first time at the IAS, and I'm just blown away at how beautiful it is. And it's wonderful to be visiting this community, so thank you for having me. So as Tomer said, I'm going to tell you a little bit about the Milky Way stellar halo today, and I want to kick off today's informal seminar with an anecdote. So when I was still a graduate student at UC Santa Cruz, I went with my now husband to this barbecue. He's in tech, and so it was for his boss. And we went to this like very fancy house in the Silicon Valley. And his boss's husband was one of those guys who, did a physics PhD and then went into venture capital and was pretty sure he knew everything there was to know about physics and academia. And so he asked me, what do I work on? And I said, oh yeah, I study the Milky Way. And his response was like, oh, well, that hasn't been studied enough, right? And I was like, 1, you're very rude. And 2, and I explained this to him, well, it's actually really important that we study the Milky Way because we have this special view of this singular galaxy that we can study on a star-by-star basis from the inside. It's the only galaxy that we can do these very careful studies of individual stars from the inside. And it's also extremely difficult because of our position within the galaxy. So it's much easier, to see what Andromeda looks like from a more holistic perspective when we're looking, say, next door. But within the galaxy, it's historically been very challenging to get a complete picture of what's going on in our galaxy. So the Milky Way, while being very difficult to study, is extremely important to study and provides the highest resolution test possible for our understanding of galaxy formation and evolution because we have this high resolution picture. So I explained this to this guy and he was like, oh, I guess I've never thought about that before. And I was not surprised that he hadn't given everything as much thought as he had thought. Okay. So the particular component of the Milky Way that I'm interested in is the component known as the stellar halo. So this is a little bit more difficult to see in an image of the Milky Way, like the previous image, which was from the Gaia satellite. So here I'm going to show you a simulation. This is from the Latte suite of cosmological zoom-in simulations, where we have a Milky Way analog, where we have a spiral galaxy that's embedded in this huge halo of dark matter, which we can't see, of course, but strewn throughout this dark matter halo are stars. So this diffuse yet also structured component is the component known as the stellar halo. And we think the Milky Way got its stellar halo through the accretion of dwarf galaxy. So in our cosmological paradigm, we think the Milky Way assembled this massive dark matter halo over time by consuming smaller dark matter halos, many of which contained dwarf galaxies. And so this is a simulation from 2005. That's an amazing simulation suite that I still use from Bullock and Johnston, where we're seeing what it looks like when you throw a dwarf galaxy onto a Milky Way-like parent potential and how these evolve in time. So what I want you to take away from this movie is that this stellar halo that's made up of many different dwarf galaxies, it's highly structured because the timescales are so long in the stellar halo compared to the age of the universe and the age of the galaxy, that these structures tend to be very long-lived. So the kinematics and positions of these stars can be used to trace back to their initial conditions. And then furthermore, as Tomer teased, we have chemical information too, where the chemical properties of these stars
have imprinted on them the formation environments in which these stars formed. So the goal of many halo studies is to use these positions and velocities and chemical abundances to reconstruct the populations of dwarf galaxies that built up the Milky Way over time. And this is, of course, not just a theoretical concept. This has been borne out in observations. There are some amazing images from the Sloan Digital Sky Survey. These are called the field of streams images, where when we look out into our galaxy stellar halo, we see the same highly structured, streamy stellar halo. So this large structure here is the Sagittarius stream. It's the most massive stream in our galaxy. We'll talk about that a lot today. We also have these smaller, thinner streams. This is GD1, and we think more of clusters. So the goal, as I mentioned, is to use these streams and systems and to study the distributions of the properties of stars to learn about the galaxies that built up the Milky Way stellar halo. So I want to take a step back and sort of talk about, I'm going to tell you a lot about my specific interest in the stellar halo, but make the connections to why I think the stellar halo is interesting for the broader field of astrophysics and how it might be connected to questions that you are interested in. So one of the big questions that we're trying to get at with studying the stellar halo is the nature of dark matter. So because stellar halos are out orbiting in the dark matter halo of our own galaxy, they can be used to trace the underlying mass distribution in the Milky Way. So how is dark matter distributed within our own galaxy? How is dark matter clustered on small and large scales? These are all questions that we can get at by studying the stars strewn throughout our own galaxy's dark matter halo. Similarly, we can study galaxy evolution because the Milky Way is not just one galaxy, as I explained, right? It's built up its halo through many, possibly thousands of systems on a large range of mass scales over a large range of periods in the universe. So we have access to these different galaxies at different periods in the universe that we can study with their individual stars, provided we can reconstruct them from because they've been disrupted. Similarly, we can look at nucleosynthesis, how heavy elements are produced and dispersed in the universe in a range of galactic environments, because we're studying many, many different galaxies. And then finally, we can also do near field cosmology. So smaller galaxies are believed to be potentially the dominant contributors to reionization, at least significant contributors to reionization. And so by studying and reconstructing these early systems that fell into the Milky Way at high redshift, we can study these high redshift, low mass galaxies that are disrupted in our galaxy, in addition to the resolved dwarf galaxies. That's typically how you think about near field cosmology, is looking at the intact dwarf galaxies, but we can do it with disrupted systems as well. So the tools that I use to try to investigate these big questions include observations. So as Tomer mentioned, I did my PhD at UC Santa Cruz. So I did a Keck PhD, leading an observing program that I'll tell you a little bit about in a moment. So my own observations. Analysis of tailored n-body simulations. So simulations similar to the Billiken-Johnston suite I showed you already, of very specific initial conditions, modeling a couple of systems and only modeling their gravitational interactions. In addition, high resolution cosmological simulations. This is a mock image of one of these fire galaxies where we can study a range of different Milky Way-like galaxies in a realistic, if not reality, environment. And then finally, with the next generation and current large-scale surveys of the Milky Way, so this includes spectroscopic surveys like SDSS-5, as well as future photometric and astrometric surveys. Currently, we of course have Gaia, and then looking forward to Rubin Observatory's LSST. And so I do want to take a moment to acknowledge all of the amazing people that I've collaborated with on these four different toolkits. I also wanted to emphasize in bold the folks who, many of these people are now postdocs, but who worked with me when they were students, and I've highlighted the contributions from undergraduates in bold italics. I'm very lucky to work with such wonderful collaborators on these projects. So I want to start by talking about the observations, and I want to talk about how we actually measure the motion of stars, because this is a topic that is near and dear to my heart and was the focus of my PhD. So when we want to measure the motions of stars in the Milky Way stellar halo, we need to measure the three components of motion in order to get the full picture of how the star is moving in space. So first, simply we can measure the line of sight velocity, so the velocity of the star towards and away from us. from a spectrum. So of course, the absorption lines will be redshifted if the star is moving away from us and blue shifted if the star is moving towards us. But then of course, we need the other components of motion. So this is what we need proper motion for. So to illustrate how proper motion works, I'm showing you this GIF of Barnard star, which is the highest proper motion star known in the galaxy, where from the simplest perspective, you take an image of a star, you wait a while, you come back, you take another image, and you see that it's moved. So this star, we can see it's moving with respect to this mostly stationary-ish background of other stars. But what if we want to measure the proper motions of these stars that don't appear to be moving very quickly? What if we want stars that are even fainter than can be seen in this image, which are most of the stars in the galaxy? So I want to highlight how we do this with HST. So in order to measure proper motions with HST for very faint stars that are much fainter than we could see in that GIF, for example, we need a stationary background source. And so what we've done in HST is develop methodology for measuring proper motion using distant galaxies as background sources. So there's a lot of HST imaging out there with multiple epochs of observations, primarily targeting distant galaxies. But if we combine these different epochs of observations, we can then study the stars too. To show you how this works, this is what's a movie illustrating how they did this for M31, the Andromeda Galaxy, where they measured the motions of the stars with respect to this distant galaxy reference frame. And so this measurement, because we were looking at M31, there are many, many stars in this image, which means you get an extremely precise estimate of the proper motion of M31. And so the precision in this measurement, this is a really weird analogy, but I really like it, is equivalent to the precision that needed to watch human hair grow on the moon, which I think is pretty cool. So this is work from Tony Sohn back in 2012. But one thing that was realized by my PhD advisors and collaborators when this study came out was that this image doesn't just contain stars from M31, it also contains stars from Milky Way, because there's the Milky Way halo in between us and Andromeda Galaxy and M31. So this was actually my first paper, the focus of my PhD thesis was the Halo 7D survey, where we took very deep Keck spectroscopy of these very distant halo stars that had multiple epochs of HST imaging, where we could use this distant galaxy wallpaper to measure proper motions of distant stars in the Milky Way halo. And I want to just mention that this was work for my PhD, but recent graduate student Kevin McKinnon just released last year a paper on the chemical abundances of these stars. So please check out his work. So we did this for, my first paper was for these stars that were between us and M31. And this was a total of 13 stars. And so this is in 2016, first paper that I wrote as a PhD student. And I gave a lot of talks on just the motions of these 13 stars. And that's because these were the first 13 stars outside of the immediate vicinity of our sun to have these measurements of 3D motions. At the time, the only stars for which we could measure proper motions, in addition to radial velocities, were located in the immediate vicinity of our sun. So this was exciting that I had these 13 stars that were much farther out than we had previously measured had these measurements for. But fast forward to today, we now have the Gaia mission, which has measured the proper motions for over 1 billion stars in our galaxy. So I say that just to demonstrate how much tremendous growth there's been in this field over the course of my career so far. To go from 13 to 1 billion, thanks to Gaia, is pretty incredible. So Gaia has completely revolutionized the field of dynamics in the Milky Way and our understanding of the Milky Way's chemodynamical structure. It's been a tremendous survey, and it's still going strong. So I'm going to tell you about some results from Gaia later, but I just want to flag, for an updated view of what we see in the stellar halo compared to the field of stream images. I could highlight a few streams in the field of streams, but this is a map of stellar streams in the Milky Way from Gaia DR2, which is pretty incredible. We've come a long way just in the last few years, thanks to these large surveys and these big missions. So we've had these tremendous advances in the data over the last decade. And I want to highlight that we've also had tremendous advances on the simulation side. So in tandem with these advances in the data, we now have these zoom in, high resolution cosmological hydrodynamical simulations. So this is a much fancier movie than the first movie I showed you, right, of dwarf galaxies getting thrown onto a Milky Way-like potential. Here we can, consider the cosmological context of a Milky Way-like analog. We can look at disk halo interactions. We can look at dwarf galaxy interactions as they're falling in. So these, of course, are not reality. There are a lot of assumptions and prescriptions that go into these simulations, but they let us study the formations of stellar halos in a more realistic setting. And for me, what I really like about using these simulations is that we can use these simulations to figure out what questions we can and should be asking of our data, because we can test and build these sort of new analysis procedures and test them in the simulations to validate our interpretations of the observations. So that's sort of how I like to work, is to hang out in the data for a while and then try some things in the sims to see if the question I was asking even makes any sense once I'm in the sims, and then go back to the data. That's how I like to work. So for the remainder of my time today, I'm going to sort of split my talk into two parts. So I'm going to tell you a little bit about my work on the dark matter wake induced by the Large Magellanic Clouds. We're going to start by focusing on the dark matter side of the four-phase diagram I showed you. And then in the second part, I'm going to tell you a little bit about chemical cartography in Sagittarius. So I kicked off this talk by showing you this beautiful image of the Milky Way from the Gaia satellite, but I neglected to introduce two very important features of this image, which you can see right here. These are the two clouds known as the Large and Small Magellanic Clouds. And while they look decently small in this image, we actually think they're very important in having a very significant effect on the Milky Way. So the Large Magellanic Cloud is the Milky Way's most massive satellite. It's orbiting at a distance of about 50 kiloparsecs. And there was this classical picture of the Milky Way LMC system where the LMC was estimated to be about 10 to the 10 M-sun, so that's about 1/100th of the mass of the Milky Way, and was just happily orbiting around the Milky Way on an orbit lasting about 2 gigayears. But that picture was conceived in a scenario where we only had one component of motion measured for the LMC. We only had the line of sight velocities. We hadn't measured its proper motion because it's pretty far away at 50 kiloparsecs. It's a difficult measurement to make. So there was a significant paradigm shift in our thinking about the Large and Small Magellanic Cloud as a result of measurements from Nitya Kilabayalo, who's a professor at University of Virginia, in 2013, where she measured the proper motion of the Large Magellanic Cloud using HST. And what they found was that the LMC's total velocity was so much faster than they thought initially, that the total velocity is too fast for the LMC to be on this happily circular orbit. It's near the escape speed of the Milky Way. And so this led to a revised picture that the LMC is not happily orbiting the Milky Way on this circular orbit at 2 gigayears, but rather is falling into the Milky Way for the first time. In addition, there is mounting evidence that the LMC is likely much more massive than we thought, probably on the order of at least 10 to maybe as much as 20% of the mass of the Milky Way. So this is a much more significant interaction than previously believed in this 1 to 100 picture that we had initially. But there's a lot of evidence in favor of this paradigm, including the LMC's rotation curve, arguments based on abundance matching, its satellite population.
This will be total mass.
Sorry?
Total mass.
Total mass, yes, not stellar mass. So the stellar mass is on the order of a few times 10 to the 9. So this, as a consequence of this revised picture where the LMC is falling in for the very first time and is much more massive than previously thought, this is a big revision to our understanding of the state of the Milky Way. The Milky Way is not sort of a happy equilibrium galaxy, but is actually undergoing this major interaction right now. And so one consequence of this massive LMC falling in for the first time is that it is predicted to have induced a dark matter wake in the Milky Way's dark matter halo. And so what do I mean by that? Here I want to highlight, this is a beautiful figure, and this work has really been, dark matter wake stuff has really been led by my colleague Nico Garavito Camargo at CCA. This is a figure from one of his papers, where he ran these very high resolution simulations N-body simulations of just a large Magellanic cloud falling into a smooth Milky Way halo. And even though it's a fairly straightforward setup, it's just two objects and they're dark matter halos and it's all N-body. The behavior in these simulations is extremely interesting, even though it's only two sources. So what he found is that as the LMC falls in, there's this wake. This wake has two components. So in this figure, this is the location of the Milky Way disk. And this is the orbital path of the LMC. So the LMC's present day position is right there. And the contours are showing you over and under densities. So what he found was that there is this over density trailing the LMC in its past orbit. So this is sort of the classical dynamical friction Chandrasekhar wake, where the gravitational particles are feeling sort of the direct the dark matter particles in the Milky Way halo are feeling that direct influence from the LMC and are form this conical wake trailing the LMC in its orbit that is exerting an effective drag force on the satellite. Then we also have this opposite overdensity opposite to the LMC in its orbit. And this is the global response of the Milky Way's dark matter halo responding to the LMC's influence.
So that must depend on what you're assuming for the origin of the coordinates. Are you taking it to be the center of the Milky Way disk or the barycenter or?
Great question. And the question that is, I think, for everyone who works on this, it's like the question is, how do you center? So for the purposes of it, basically everything I'm going to show you today, we're centered on the Milky Way disk, assuming that we're moving with the Milky Way. But you're right that it's not the barycenter. So I'll show you a movie to illustrate that right here. So we have these over and under densities as a result of the LMC falling in, but we also have this significant perturbation to the barycenter where the LMC is falling in, and in these simulations, what it's done is displaced the inner halo of the Milky Way and the Milky Way disk from the overall center of its dark matter halo. And so we have this sort of shifting barycenter as a function of distance, and the Milky Way is no longer centered in its own halo. So we have these over and under densities that are affecting the potential in our galaxy. And then we also have this complete shift in the center.
The over under density is calculated relative to the time zero density profile or the shifted one.
The time zero. Yes. Yes, that's correct. So some of that global response is a result of that shift. Yes. Great, thank you. Okay. So because the potential of the overall system, even though we're only looking at the Milky Way and the LMC, has been so affected by this interaction, the stars in the halo are going to respond to the fact that they have this perturbed potential. So we can use the motions of halo stars in these simulations to trace the wake and identify the signatures of the wake. So these are velocity maps of stars in these simulations, which are again N-body, LMC, Milky Way only. So these are the maps of the average velocities in the three components of spherical motion. So radial velocity is here, polar velocity is here, and rotational velocity is on the far right. So this is like a projected on-sky map of the different velocities, and this is on a shell centered on 45 kiloparsecs in the galaxy. And so the LMC is shown by the position of the LMC is shown by the white star. And so we can see if we look at radial velocity, for example, immediately trailing the LMC in its orbit, which is currently moving out away from the Milky Way, we have this sort of a yellow patch, right? So these are the stars that are following the LMC in this Chandrasekhar wake out of its orbit. Sorry, I mean to hit the screen. There we go. Similarly, there's this dark blue patch, which are stars that are moving towards the Milky Way that are also trapped in this wake that's trailing the LMC in its orbit. Similarly, we see these converging motions here and here in these velocity maps for the stars that are feeling that direct gravitational influence from the LMC. In addition, we see this we see the imprint of what we call the reflex motion, which is the fact that the Milky Way has moved with respect to its center of mass in its dark matter halo. It's experiencing this net downward motion. So what that means is that stars in the south are on net moving towards us, and stars on the north are net moving away from us. And we can see this because the top of this radial velocity map is yellow. These stars are moving away from us on average. And it's hard to see in this particular map because we have the features due to the local disturbance, but the south is moving towards us. Okay. However, this is a really exciting theoretical prediction that we would like to be able to investigate, right? There's one major complication, there are a few major complications, but one I want to highlight is that we don't think that the Milky Way is this smooth, idealized halo that we were using in the simulations. We think a halo is made up of disrupted dwarf galaxies, disrupted dark matter halos, and that, as I mentioned at the beginning of this talk, are very structured and tend to have these very long-lived structures. So because in particular the stellar halo is made up of these streams and structures predominantly, it could be very difficult to resolve these signatures from the LMC wake. So as an example, I'm showing you what a velocity map looks like from the Bullock and Johnston simulations. This is just the radial velocity map. But in the previous slide, these color maps are showing you plus or minus 40 kilometers per second. This particular Bullock and Johnston halo, the color bar is going from minus 200 to plus 200, right? So we could get this very dominant, potentially dealing with very dominant signatures from galactic substructure. However, these features are in general more smaller scale and the wake signatures are larger scale. So what we sought to do back in 2020, me and Nico, was to test if we could use spherical harmonics as a tool to disentangle the velocity fields of the stellar halo and identify signatures due to small scale perturbations like galactic substructure or larger scale perturbations like the dark matter wake. So to illustrate how this works, here I'm showing you again, these are radial velocity, the three components of spherical motion maps from Nico's simulations of just the LMC and the Milky Way, where the top is the raw simulation data for 45 kiloparsecs. And the lower panels here, I'm showing you the L=5 expansion of these velocity maps. And we can see that a very low order expansion is doing a very nice job of identifying all the salient features that we were interested in, right? We have a dipole, we have the Chandrasekhar wake here, and here they're converging motions, etc. So this is great. But what happens if we add some, and there's one other feature that it encapsulates really nicely. So I mentioned this effect of the south moving towards us and the north moving away from us. What we see is that this effect increases as a function of distance, and we can quantify this very nicely through the magnitude of the dipole mode when we quantify the radial velocity. We characterize the radial velocity maps with spherical harmonics. So here I'm showing you what the power in the dipole, the total power in the dipole as a function of radius out to the halo is for different LMC masses that we simulated. So that is all well and good. But what about this question of galactic substructure? So what we did was that we decided we could compare the power spectrum of the velocity fields with the LMC only simulations and compare it with the Bullock and Johnston simulations, where there are no dark matter wakes in those simulations because they're just dwarf galaxies thrown onto a Milky Way like current potential. There's no live dark matter halo. And so we took the extreme accretion histories from the Bullock and Johnston suite. So this is a velocity map of a halo that's made only of very luminous satellites compared to a halo that's made up of only very low mass satellites. In contrast, we can look at a halo made up of only recently accreted materials, only substance fell in the last, 6 gigayears, compared to a halo that was assembled very, very early on. And so on the far right, I'm showing you the power spectrum for each of these sort of extreme accretion histories from Bullock and Johnston in comparison with the range of power spectra for the LMC, the suite of LMC only simulations. So they had 4 masses, that's why that's a purple band in this image. And what we find is that at low order, looking at L=1, L=2, the dipole mode, in particular is what we need to resolve for the reflex motion, is that the LMC is generally causing higher power at these lower modes with, 2 really big exceptions. And it's these 2 maps right here. It's the halo made only of recently accreted material and halo made only of very massive satellites. So our sort of takeaway from this was, okay, we think if we're doing, spherical harmonic expansion, the dominant contributor at low order, so for the L=1, L=2 equals 0, should be, dominated by the LMC in the Milky Way, unless we're worried about, accretion from unless we're worried about debris from recent high mass accretion events. So fortunately for us in the Milky Way, we think it's had a relatively quiescent recent accretion history with 2 major exceptions. The first of which, of course, is the LMC-SMC system. There's this massive interaction going on right now. And then the second is Sagittarius. So the Sagittarius stream is the most massive stream in Milky Way. It has debris all over the sky. Figuring out what to do about Sagittarius debris is something that many Milky Way halo people, myself included, think a lot about. But this is sort of the biggest challenge in terms of, this is the accretion event that we expect to be the biggest problem for finding that LMC signal, the signal to the LMC. And so what we did back in 2020 was we said, okay, what happens if we inject a Sagittarius stream? We can just literally assume it's 10% of the mass, put it in the simulation, and see what happens to the power spectrum if we include a Sagittarius. There are caveats to why I have feelings about this now that I'll tell you about later in the talk. But what we found was that in general, Sagittarius can contribute significantly to the lower order modes in the power spectrum, but it's not killing the signal. But it's still predicted that the LMC signal would be dominant over the signal we expect from Sagittarius. But we should definitely model it because Sagittarius is a big enough system in the galaxy that it can be contributing significantly to the low order modes.
Can you just exclude these contaminants like?
Yes, so that's a great point that we can. This is assuming that we just keep all the Sagittarius stars in, and we don't have to do that because we know where a lot of them are. However, I'll show in just a few slides how it is a little trickier to do than we think. So those were sort of our results from 2020. And on the observational side, since that paper came out, there have been a few really exciting discoveries that I want to highlight. In particular, this is work from Charlie Conroy. This came out in Nature, where they argued that they have found the LMC wake both trailing the LMC in its orbit. They found overdensity in its orbit, as well as this overdensity on the opposite side of the galaxy. In addition, there's been work from Mike Peterson and Jorge Penarrubia detecting this net motion, the reflex motion of the Milky Way, which is really exciting and interesting. But I want to have a few words of caution because I think there are a few things we still need to work out. In particular, we haven't yet cleanly identified a dark matter wake in a cosmological simulation. There are people working on it. We will figure it out. But in my opinion, it's really important that we cleanly identify these signals in the cosmological simulations, in these cosmological halos, so that we know we can trust our interpretation of the observations. So this is work that I started with Alex Riley, who's currently a postdoc at Durham. He worked with me at the Big Apple Dynamic Summer School we held back in 2021 at CCA. And what Alex is doing is taking fire simulations that have an LMC analog, an analogous interaction to what we think is going on with Milky Way and LMC, and is looking for this net reflex motion, this velocity dipole. And what he finds is that when he looks at a fire galaxy that has a massive satellite similar to the LMC, he finds a velocity dipole that increases with distance, which is exactly what we see in the LMC only simulation. So that's reassuring. However, if you have a system that doesn't have an LMC, but it has a massive stream, the massive stream can cause similar signatures if you're only looking in one radial range. So I should have clarified that before. The current observational results that we have an estimate for the reflex motion at one number at one radius in the Milky Way. We just have one number to encompass everything that's going on. So this is something that you could see as a result of galactic substructure. For me, it's the increasing as a function of radius signature that is very convincing as a signature of the reflex motion. Similarly, I've also recently revisited this in a project with Jo Verwold, who is a graduate student at the University of Copenhagen, currently visiting me she visited me in the fall and is currently visiting for a couple of weeks, where we've looked again at the stars that have been used to measure the reflex motion of the Milky Way. And we find that when we compare their properties with Sagittarius members, they did an initial cut to try and eliminate some Sagittarius members. But a lot of these stars are still, when we compare to a modern simulation of Sagittarius, they're still lying very similar. They have very similar properties to what we expect Sagittarius to have. And one challenge of this that I didn't mention, that I didn't take into account in 2020, is that we think Sagittarius is actually the dominant progenitor of the outer stellar halo. It's the major thing out there in the stellar halo. So it's actually much harder to subtract off and actually leave you with a lot of signal because it's the main source of stars out there, to our knowledge. So we're working.
Do you have any estimation of when it?
The Sagittarius interaction, yeah, so we think Sagittarius fell in about 6 gigayears ago. There's a lot of uncertainty on that as well. So it's been disrupting for many times, so it's wrapped around the galaxy multiple times. And its orbit has been perturbed by the LMC, and so it's not easy to cleanly select Sagittarius in the outer halo. Yeah. But looking forward, so Joe and I are working on developing some different ideas for modeling Sagittarius contribution to reinvestigate that measurement of the reflex motion. But looking forward, I think this is a problem that is really exciting for the next generation of large-scale surveys, in particular. Rubin Observatory's LSST is going to get these wide field, deep proper motion maps of the galaxy, and combined with Roman Space Telescope, we'll get very precise proper motions of particular regions of the galaxy. And so I think getting these large-scale views of the kinematic structure of our galaxy in conjunction with very precise proper motions in key areas will help make a lot of headway on this problem. So just to conclude part one, the LMC is predicted to induce dark matter wake in the Milky Way's halo, and we can use spherical harmonics as a tool to disentangle contribution from substructure. In particular, we need to worry about recent massive accretion events if we're looking at things like the dipole mode, for example. But we've done some tests with Sagittarius, and we think it should be modeled. But to me, worrying about Sagittarius is a challenge in this problem going forward. And looking forward, I'm highly in favor of testing these things in cosmological simulations. And we're going to get a ton of data to really get at this problem in tangential motion with Rubin Observatory and Roman Space Telescope. So for the remainder of my time today, I want to talk a little bit more about Sagittarius. So as I mentioned, Sagittarius is the most massive dwarf galaxy stream in the Milky Way. Debris all over the sky. We think the progenitor had a total mass of something on the order of a few times 10 to the 10 solar masses and dark matter before it fell in. But because it is this massive system and it has debris all over the sky, historically it's been a favored tool for constraining the dark matter shape of the Milky Way and mapping the dark matter potential of the Milky Way. So this is a sort of a famous study from Law and Majeski 2013, though there have been a number of updates on using Sagittarius to trace the Milky Way's dark matter halo distribution recently. And we have a lot of amazing simulations. In particular, I want to highlight this work from Eugene Vasiliev, showing that we can reproduce a lot of the features of the Sagittarius stream, in particular if we include the influence from the Magellanic Cloud, which is what Eugene did in this paper, and the LMC comes in. So Sagittarius has historically caused a lot of problems for observers, and recently a number have been, sorry for theorists, it's caused problems for observers too. Sagittarius causes lots of problems, but a number of the features of the stream have been difficult to reproduce, but a few of these problems have been, mitigated when you include the LMC interacting with the Sagittarius stream. But there remains a lot of uncertainties on this interaction. So you asked, when it fell in. Well, we start modeling it sometimes, 3 gigayears ago. We think probably 6 gigayears ago, but the models that started 6 gigayears ago aren't reproducing the observations yet, because that's a long time to rewind back and actually get a realistic model for the stream. And there is a lot of uncertainty on the initial mass of Sagittarius as well. But if we're going to use this system to model our Milky Way's dark matter halo, we want to do whatever we can to constrain the initial conditions of this interaction. And so one tool at our disposal is stellar metallicity. So stellar metallicity is known to correlate with total stellar mass in the local universe with local dwarf galaxies. So we could play this game. But one kind of funky question is that Sagittarius is actually quite metal rich. So here I'm showing you metallicity distributions for a few dwarf galaxies. So this is Fornax, this is the SMC, and this is the LMC. And this histogram I'm showing you Sagittarius in the core Sagittarius. So in that intact dwarf galaxy core, excluding the strewn stars. We can see that it's actually quite metal rich. And I've spent a lot of time telling you how we think the LMC is really massive, and you'll note that the core Sagittarius is actually significantly more metal rich than the LMC, which is interesting. So from this, you might think, well, maybe Sagittarius had a really, really high initial mass. It's more massive than the LMC. However, we have to be careful when playing that game because we know that Sagittarius has a metallicity gradient. And so this has been observed in many local group dwarf galaxies. It's observed in Milky Way as well, but this is some work from the Pristine survey, where what they found was that they looked in radial bins extending out from the core of Sagittarius, that the fraction of metal poor stars relative to metal rich stars increases as you go out, which means your mean metallicity is decreasing as you move farther from the progenitor. So if we actually want to know the initial metallicity distribution of Sag, we have to think about all of the stars that have been stripped and then rewind it back into the original progenitor before disruption. We can't just take the metallicity in the core and then assume we know its mass. So there's been some interesting work of incorporating the stream component into studying the metallicity structure of a Sagittarius dwarf galaxy. This is work from Chris Hayes using Apogee, where Chris measured these gradients as a function of Sagittarius longitude. So this is longitude along the stream. And he found these gradients, in particular, the leading arm is more metal poor relative to the trailing arm, which is interesting. But one thing you might note that could be a challenge when you're looking at this particular pod, and this is something that plagues all chemical studies of Sag stars so far, is that there's actually not a lot of stars in the stream that have these measured chemical abundance information. We're limited by maybe a few hundred at most in each arm. And in addition, you can see that it's kind of incomplete coverage along the stream, right? Because these are Apogee data, so this is quite expensive. You have to point intentionally out into the distant stream to really get a decent sampling of stars in the stream.
What is the significance of this trend?
So this is definitely.
They look like clouds to me.
Yeah, they do look like clouds. So I don't remember the exact errors on this, but I can show you them on my measurements, which are coming up. How about that? So inconsistent with 0 for sure. But they found more consistent with 0 if you leave out the core. So these are the stars in the core of the dwarf galaxy. But yes, they're diffuse, significant scatter, diffuse, not a lot of stars. So one tool at our disposal for studying the chemical structure of the stellar halo is Gaia. So one of the really exciting data products from the Gaia data release 3 are these BP-RP spectra, or what they're called, they're very low resolution spectra that a number of groups have shown actually contain significant information when combined with intelligent machine learning models and the correct training sets about the chemical abundances of stars in the halo. And so what I did last year was make a metallicity map of the Sagittarius stream using data from the Gaia TR3. So this is my map of the stream, where this is only showing the inner wrap, the first wrap of Sagittarius, where the sun is here, the Sag remnant, so this is the intact dwarf galaxy, is located right here. The galactic midplane is shown by the dotted line. So this is the trailing arm of the Sagittarius stream. These are stars that are chasing Sagittarius in its orbit. And this is the leading arm. So this is stripped debris that's ahead of the Sagittarius dwarf galaxy in its orbit. And for these metallicities, I had a total of 34,000 stars that are red giants in the Sagittarius stream, using a selection from Eugene Vasiliev, and combining for the experts, use the Gaia BP-RP metallicities measured by Renee Andre. And so I want to emphasize that this is, over an order of magnitude more stars within Sagittarius with chemical abundance information than we've had before, right? So Gaia DR3 is really blown open what we can do with chemistry in the halo. Very low resolution, individually uncertain, yes, but with these huge numbers, we can actually do a lot with this sample. So I can also show this projected in Sagittarius stream coordinates. So this is Sagittarius stream longitude, or lambda. So the satellite is moving this direction. And this is Sagittarius stream latitude. So we can see the stream is pretty thick on the sky. The remnant is located here at approximately 00. These bright yellow spots here, these are very metal-rich stars. This is Milky Way disk contaminants in the sample. Fortunately, they light right up when we look at them in metallicity, which is very useful. And we can look, just like Chris Hayes did, as a function of stream coordinates using this sample. So here I'm showing you mean metallicity as a function of stream longitude in the lower panel. Similar to Chris's work, we find it's decently flat in the leading arm. This uptick, I think, is mostly due to contamination from the Galactic Center. I'm sorry, this is the trailing arm. In the leading arm, we see this steep decrease and then this relatively flattened out period of overall lower metallicity in the leading arm. So broadly consistent with what Chris Hayes found, but what was new was that because we had these big numbers of stars, we were able to look not just along the stream, but across the stream. So we observed a gradient in stream latitude for the first time that was just not detectable in previous samples because they didn't have the numbers in order to resolve what was going on up and down across the stream like this. So this we observed for the first time with this sample. And so in order to interpret this and to figure out what do we learn from this, okay, we see this gradient across the stream. What does this even mean? We compared with a suite of simulations run by my colleague at CCA, formerly at CCA, now at Surrey, Jason Hunt, and Ioana Stalea. Ioana actually really ran these simulations. She is a starting grad student at University of Wisconsin-Madison. But they ran a series of simulations, extremely high resolution simulations of a Sagittarius-like perturber onto a Milky Way-like disk, and also including a large Magellanic Cloud. So the purpose of their work was to study the influence of these perturbers on the disk of the galaxy. But we, of course, get models of the stream for free, for me, free for me. And so what we wanted to do was, compare, see if this sort of gradient perpendicular across the stream was predicted in the simulations and what we might. So here I'm showing you now a map of the simulated Sagittarius stream, where again, the core is centered approximately at 00. This is stream longitude, this is stream latitude. And instead of color coding by metallicity, I'm color coding by initial radius within the Sagittarius dwarf galaxy before disruption. So these stars are all really tightly located in the galaxy initially, while as these stars are more located farther out initially, which all is to be expected. But when we decompose this into trends with stream longitude and stream latitude, we actually see trends that look extremely similar to what we observed in the data, where in particular, if we focus on, we see stream longitude trends, as well as a stream latitude gradient of initial radius within the progenitor. So what we did was we painted metallicity gradients onto this simulation. We kept it all very qualitative because, as I mentioned, the purpose of these simulations was to study the disk. So it's not a perfect Sag model. All the properties aren't perfectly aligned. In particular, the orbit of the progenitor is at a slightly different phase compared to the observations. But, qualitatively, if we have a flat metallicity gradient, it's completely inconsistent with the data. If we paint on a metallicity gradient of -0.4 dex per kpc, it's clearly too extreme. It's not reproducing the trends, but something in the range of -0.1 to -0.2 dex per kpc is in very good agreement with what we observe in the data. So what do we do with this information? Oh, and I also just want to mention that metallicity gradient is perfectly in line with what we observe in local group dwarf galaxies. So this is, not a crazy number. This sort of lore that Sag must have had this elaborate star formation history in order to reproduce its chemical properties, but its gradients are pretty consistent with what we're observing locally. So what might we learn from this? We don't directly get the mass out yet, unfortunately, but one interesting thing that I think could be done with this data set that I want to highlight, I keep putting this out into the world, hoping that somebody does it, or maybe eventually I will do this, is investigating the question of whether or not the Sagittarius dwarf galaxy had a disk. So this is one theory that's been put forward to resolve this question of this, it's called the Sag bifurcation. The Sagittarius stream has these sort of funky crab claws. It has this very bizarre morphology. And I think I usually show a slide and I didn't today, which is why I'm making crab claws with my hands instead. But it's this outstanding problem in modeling the stream that's been a big challenge for the modeling community to reproduce. And there have been a few papers arguing that potentially a disk structure and a rotating structure could reproduce the bifurcation. But if you have a disk dwarf galaxy that has a metallicity gradient radially that's distinct from its vertical metallicity gradient, the orientation of that disk and magnitude of those gradients will affect the metallicity gradients you observe in the stream. And so I think painting gradients onto simulations that include a disk of Sagittarius, or even identifying stars on disk-like orbits and seeing what happens when you play with the different metallicity gradients, seeing if this picture is consistent with the data would be interesting on this particular question. So just to summarize for part 2, we have this chemical map of the Sagittarius stream. These catalogs, this cross-match catalog is all publicly available, so feel free to grab it and play with it if you're interested in it. We detected a metallicity gradient across the Sagittarius stream for the first time and found that the Sagittarius dwarf galaxy likely had a metallicity gradient of between 0.1 and 0.2 dex per kc prior to disruption. So for more details, please check out our recently published paper. And thank you very much for your time.
Thank you, Emily. We have 7 minutes for questions.
For the first part, like about the spherical harmonics, like sometimes, I mean, I guess these distributions, they look like elongated, so aren't like wavelets or something better than using spherical harmonics?
Yeah, absolutely. So that was one lesson we learned, that spherical harmonics, particularly on the substructure side, are not necessarily the right basis. So I think moving forward I think the next step would be playing with other bases for identifying the streams and characterizing the streams is absolutely right. Yeah.
To what extent do we have good 6D data for Sagittarius?
Yes, so that is a complicated question. Part of it depends on the stellar population, right? So we have very good 6D data. We have decent, so I was looking at giants. I would say probably giants are where we're at the best with the 6D data. For our library, we get really precise distances, and we mostly don't have RVs for those. And so I've looked at this a little bit it's also bothering me that there is debris from Sagittarius that I feel like should be there that hasn't been identified yet. Like the leading arm is supposed to come back around and we haven't seen where it comes back around, and where the trailing arm ends is still open. So I think those debris actually from the earliest drooping events will be very constraining for its past interaction for the Milky Way, but we haven't found it yet. Does that answer your question?
Yeah, I just have this idea, which might be completely ridiculous for observers, but trying to work out whether Sagittarius have disk.
Yeah.
And if you could somehow calculate the maximum phase space density of Sagittarius today, that cannot be larger than what it was initially. So if it's some large value that's inconsistent with having a fluffy Sagittarius, then it had to be packed into a disk, basically.
Great question. Great question. That would be really cool to talk more about.
I'll ask a question. In your spherical harmonic decomposition, I understand that a contaminant to a Bollinger-Johnson-like simulation where everything is coming in isotropically in small mergers, you have a big merger, then that it's just like the LMC in a sense, it gives you a strong signal. What if there's some intermediate picture where you have like a plane of satellites, or you have all of the small satellites are coming in a preferential direction? Does that contaminate it in a way that is not trivial?
That's an amazing question. I bet it would be non-trivial. I would have to think that if you have a collective, if you have a large number of things moving collectively, it could contaminate. Yeah, that's a great question. That's a great point.
There's some uncertainty about the solar circular speed around the galactic center, with estimates ranging over 30 kilometers a second or so. How does that affect your conclusions about the velocity signatures of the LMC that you see in Halo?
Yeah, I think that's a really great point is, constraining our own reference frame. There's that inherent uncertainty on the motions we're measuring outside if we're not sure about our reference frame and where we want the center of the galaxy to be and how fast it's moving relative to us. So I think that's a very valid question. I haven't done the exercise. I know in the reflex motion paper, they claim to do the exercise of playing with motions for the solar circle and found that they got consistent answers, but I don't think they really put full description of that testing and analysis in the paper. So I can't say exactly how much it affects it, but I know they did look at it.
I also have a wake related question, and this situation that you showed was the Milky Way structure itself followed well enough? Because if it's not now it's sitting in the center of the potential,
Right.
What is it gonna do to the Milky Way in the long run?
Right. So in the simulations, it was just sort of an idealized disk potential. There wasn't, a real live stellar disk that we
Oh,
could
so
play
it
with.
wasn't the real.
Yeah, so I think personally on the n-body side, well, I'm interested in, I think they're in the tailored sense, there's a move towards including gas. And I think including gas is also really important for the Sagittarius orbit. There's only, I think, one paper so far on tailored simulations of Sagittarius, including gas, and it really does change the orbit. And I think if you have a live gas disk, that will change and how it responds, that will to the LMC, that could have more information constraining that orbital history as
And
well.
even the stellar population would be distorted.
Exactly.
And so on.
Exactly.
So nobody looked into this?
So there is work looking at sort of it's called the phase spiral I know there are a lot of people here who know a lot more about the phase spiral than me, but there are arguments that the LMC and Sagittarius could be exciting these modes in the disk. But in the simulations that we looked at, there were not, it was a very smooth idealized disk and there were not significant. In my head, now I'm actually not sure if Nico ever looked at phase spirals from his simulations. There might not have been enough resolution in the disk to resolve it in that particular suite, but I know that they've looked at this for the LMC and Sagittarius in other work where you can't get these perturbations. Yeah. We think, correct me if I'm wrong, anyone in the room, that the perturbations in the solar neighborhood are likely not driven by the LMC as much as Sagittarius. That's my current understanding, but because Sagittarius gets much closer to the disk, but the LMC can't.
Okay, last question, go ahead. Yeah.
Just for the streams you mentioned about the Sagittarius, can you do these studies with other streams? Very nice. Metallicity gradients along. And
Yeah, I think you can. I think that's something I actually have an undergraduate looking at that a little bit to see, based on the current data we have from stream stars that are stream candidates and the Gaia DR3, you can cross-match those to look for more streams with stars. One thing you fight when you're looking at a smaller stream is that you have smaller numbers of stars. And so, because especially the distant streams will only have a few giants that are bright enough to see, and you really infer a gradient from a handful of stars? No. So with Sagittarius, we have the most stars, so it's the easiest, but you absolutely could. And I think that'll be exciting for next generation spectroscopic surveys targeting streams. We'll have a lot. I know Desi in particular is going to get a lot of chemical lenses in streams.
I was just saying you could stack it and then the statistical significance might go up. But I don't know.
Yeah, you'd want to be careful stacking the different streams if you think you're looking at drastically different systems. They're one's 10 to the 5 and one's 10 to the 7. You wouldn't want to stack them.
Let's continue conversation over lunch. There are also a few slots left on Emily's calendar scheduled this afternoon, as well as some slots open for dinner. But please sign up for dinner if you want in the next hour-ish so that we can finalize the reservation. And with that, please join me in thanking Emily again.